our schedule, see where we are. Today's the 24th. We're going to talk about exponential functions. So in packet 3, you'll notice that after class 32, where class 33 is supposed to be, there's a blank page that says insert classes 33 and 34 here. I just handed out classes 33 and 34. It's a separate handout. Okay, so you should have it in front of you now. And I don't have your quiz 5 graded yet, but just to keep an eye on what's coming up. Monday, project 4 is due. Okay, so next time I see you, project 4, the student ID number project is due. And then Wednesday, I will be assigning the next take-home quiz. And then then we'll have one more test, just one more test, and the final exam. Yes. Yeah, I'll assign the take-home quiz Wednesday. It'll be due Friday, so that you can get it back the day before the test. Yeah. All right. So, any questions on upcoming schedule? Okay. It's a good question. It is, yeah. No, we had to, when they were, okay, so we're going to talk about exponential functions today. All right, so according to USA Today, there was an article that titled 2015 pay raises expected to be 3% next year. So Gary Strauss, the author, he states that US employers are planning to give pay raises averaging 3% next year. So this pay rate is similar to previous years, and it's in keeping with the average employee. It keeps the average employee's pay slightly ahead of inflation. The article also claims that the median annual salary among the nation's 106 million workers is now about $40,560. Okay, so we're going to let T represent the number of years after 2014. So 2014 is going to be year T equals 0. So 2015, next year, according to the article, next year, right? That would be T equals 1, 1 year later. All right, so S of T is going to represent the median salary T years after 2014. All right, so I want to calculate what the new median salary will be if we do a 3% raise, right? So the way you calculate the new salary is you take the old salary, the 2014 salary, and add 3% of it to itself. Okay, so you take 3% of the 2014 salary, add it to the 2014 salary. So 2014 salary was 40,560. Add to that 3% of 40,560. So it's 40,560 plus 1,217, and you get $41,777. So it's your new median salary in 2015. If the median salary continues to increase by 3% each year, okay, so when that is not a bad model, 3% increase. There are times in history where things have grown much faster, and there have been times when things have grown much slower, but 3% is like a pretty steady average growth rate. So we're going to assume that we continue to grow at the same constant percent of 3% each year. So we're going to fill in these new salaries. Okay. So I did, year 0 was 40,560. Year 1 is 41,777. And then we're just going to keep doing this each year until 2020. Okay, so in year 2, which is 2016, I have to figure out how much my increase is going to be. And my increase is 3% of what the salary was the previous year. Okay, so I'm going to take 3% of 41,777. So 0.03 times 41,777. And that's $1,253.31 is the amount of the raise. And then you have to add that to your 41,777 to the previous year's salary, and we're now at 43,000. $30.31. And then we do it again. We take 3% of that number, and that's going to be the amount of our raise for the next year. So times 0.03. And this year, our raise is going to be $1,290, and we'll say 91 cents. We'll round to the nearest penny. And add that to the previous years, 43030.31, $44,321.22. Where'd I lose you, Joe? Mm-hmm. Yep. You got a different answer? So in the next line, it should, the 40,560s should be replaced with 41,777s. So if you do 41,777 plus 0.03 times 41,777, 43,030.31. You did addition before the multiplication? Okay. All right, so then we do it again. We're at 44,321.22. And I have to figure out what 3% of that is, because that's going to be the amount of my raise. And so this year I'm getting a raise of $1,329.64 if I round to the nearest penny. And then I'm going to add that to 44,321, add that to my previous year's salary, and I get $45,650.86. Does this make sense? Okay, so I just have to do a couple more times 0.03, 1369.53 plus the previous answer. $47,020.39 times 3% to get the next year's increase, $1,410.61. Add that to the previous year's salary, and I have $48,431, almost exactly. Okay, so look at the amount of the increase. By how many dollars my salary increased each year? Is it the same amount every year? No. The number of dollars in my raise is going up every year, right? $1,250, then $1,290, then $1,329, and then $1,369, and then $1,410, right? The amount of dollars that my salary went up by is not the same every year. So the yearly salary increases are not the same. They're actually increasing. The amount of my raise gets bigger every year. So what would I expect the graph of this function to look like over 10 years? Right? Would it be a line?
No.
Why is it not a line?
There's no like difference.
Yeah, in a line, these would have to all be the same. This would represent the slope, right? The amount of change over 1 year would have to be constant. Each year would have to be constant. That's what slope is. But now, over each year, the amount of my raise is jumping by more and more and more. So instead of having a constant slope, if I plotted the year, let's see, year versus salary, the amount of the jumps will get bigger and bigger and bigger. So my first salary was like 40,000. I'm not going to plot this with any accuracy, right? And then I have a small jump, right? And then the next year I have a slightly bigger jump. And then the next year I have a slightly bigger jump. And then the next year I have an even bigger jump, right? So you see the vertical change between successive points. is getting bigger each year. The y jump is getting bigger and bigger every year. So what I end up with is actually something that looks like a curve. So these purple lines are representing the amount of my raise, right? If the raise amount was the same every year, those purple lines would have to be constant. They would be the same. So this is what we call exponential growth. All right, so the example that we just explored introduces the idea of a quantity growing at a constant percent rate. That was 3% growth for every year. Okay. Functions that increase at a constant percent rate are called exponential functions. Okay. So let's see if we can develop a general formula for the median salary example. So we want a formula for S, salary, in terms of the number of years T since 2014. So your new salary after 1 year, this is how we calculated it, right? We took our previous year's salary and we added 3% of the previous year's salary. Sort of a shortcut for increasing something by 3% is to multiply by 1.03, right? Because the 1 represents keep 100% of what you had before and then add an additional 3%. So take 103% of what your previous salary was, and you've increased it by 3%. So that's a quick little shortcut for increasing something by 3%. So after 2 years, I would take my 40,560 times 1.03, and I have to multiply by 1.03 again, right? So I end up with 40,560 times 1.03 times 1.03. Right, because that's my 2015 salary, and then I increased it by 3% again. So it actually looks like 40,560 times 1.03 squared, okay? Because I increased by 3% twice. Yes.
So you just jump 2 years, 2 years, 2 years. Change from the first spreadsheet to one.
Sure. Yeah, sure, you could. You could, yeah. But if I wanted to be even a little bit more efficient, rather than having to do this calculation out and get a new number, I could always start with the initial value of 40,560 and then just multiply by 1.03 an appropriate number of times. Right? If I wanted to know my salary after 3 years, I would say, well, I would start with $40,560, my initial salary, and I would multiply by 1.03 3 times once for each year to increase by 3% 3 times. So I would make that cubed. So for 5 years, I would just do 40,560 times 1.03 to the 5th. 10 years to the 10th. Increase by 3% 10 times. So I wanted to come up with a formula for what to do after t years. So it looks like all I'm doing for various numbers of years is I'm just putting the number of years in the exponent, right? So if I wanted a generic formula, right, my salary after t years can always be calculated by taking my initial salary, multiplying it by 1.03 t times, however many years have gone by. So you raise it to the t. So to be a little bit more general, right, that 40,560, that was my initial salary. So I could just write initial salary there instead of 40,560. And 1.03 is something we call the growth factor. The word factor is, what operation does factor have to do with? What kind? Operation. So factor, it could be addition, subtraction, multiplication, or division. Factor indicates which of those 4 operations. Multiplication. The numbers in a multiplication problem are called factors, right? So when I say a growth factor, I'm saying the number you multiply by to make it grow. Right? So I multiply by 1.03 multiple times to make my salary grow. So my growth factor in this case is 1.03. All right, so the general definition of an exponential function when you're modeling data, it looks like a times b to the t. And before I move on here, one quick thing. Could I simplify this to say s equals $41,777 to the t? Can I multiply the 40,560 times the 1.03? Why not?
It's not order of operations.
Order of operations, yes. You can't do the multiplication before you deal with the exponent. And when the exponent is a t, you can't do anything. So this is not allowed. Okay. So just want to make that clear. So you do have to write out a times b to the t. You can't multiply the a and the b. Right? A is your initial value, right? In our case, it was an initial salary. And b, which is sometimes called the base, because it's the base of the exponential, is called the growth factor. So the growth factor is always found by doing 1 plus the percent rate. So in our case, we were increasing by 3%. Our growth factor was 1.03 because you just add 1 to the percent rate, written as a decimal. If there's growth, that means that R is positive and B has to be bigger than 1. And if you're actually decaying, if you're losing 3% every year, that's called exponential decay. That happens when R is negative, and then your growth factor B is actually a number less than 1. B would never be less than 0, right?
But
A can. Yep. No, A can't be less than 0 because A is an initial amount, some quantity of stuff.
Okay, so it has to be, it can't be 0.
Right. Yep. All right, so quick note, some books define exponential functions, including our textbook, as just b to the t. They take that a value and just make it 1. They say a times b to the t. Well, the most basic exponential function has an a value of 1. And then they use transformations to explain what happens when you have different a's, vertical stretches and shrinks. All right, so here's some examples of exponential functions. So I have f of t equals 2 to the t. Is that growth or decay? As t gets bigger, will f of t get bigger or smaller? Bigger, yeah. That's going to be 2 squared, 2 cubed, 2 to the 8th, 2 to whatever. So it's going to get bigger. So this is growth. What is my growth or decay factor? What do you multiply by for each unit of time? 2. And what percent growth rate does doubling correspond to? If your salary doubles every year, don't I wish, right? If your salary doubled every year, what percent would I say it increased by? 100. It increased by 100% of itself. Yeah. You get to keep 100% of what you had, and then you get another 100% of what you had, right? So this is a 100% growth rate. Your salary increased by all of itself, 100% of itself. Okay. All right, here's another one. P of t, 100 times 1.012 to the t. Is this growth or decay? Growth. If you multiply by 1.012, it's going to get bigger, right? You're multiplying by something bigger than 1, the result will be bigger. So this is growth. What is my growth factor? 1.012. And what percent growth rate does that correspond to? 1.2%. right? The 1 in the growth rate, in the growth factor, represents you get to keep 100% of what you had, and 0.012 represents the additional percent growth over and above what you had before. So 0.012 corresponds to 1.2%. Okay? You just moved the decimal 2 to the right. 2 to the right. Okay. Okay, g of t, 200 times 0.886 to the t. Is that growth or decay? Decay, because when you multiply 200 by a number smaller than 1, it's going to get smaller, right? So this is decay. And what is my decay factor? 0.886, yep. It's because that's what I'm multiplying by. Factor means the thing you multiply by. Okay. So what kind of percent changed does this represent? Yeah. This represents, we're taking 88.6% of what we had before, right? Multiplying by 0.886 is like saying, well, let's figure out what 88.6% of 200 is, right? So that's how much you get to keep, which means that you are losing, say it again, is it 12.4 or 11.4? 11.4, yeah. So my constant percent rate of change is negative 11.4%. I am losing 11.4% each year. So think of 0.886 corresponds to 88.6%, right? This is the amount we are keeping. Okay, so we take 100%, subtract what we get to keep, and you end up with 11.4%, and that's how much you lose, right? You start with 100% of stuff, you get to keep 88.6% of it, so that means you are losing 11.4% of it. Okay, so the graph of exponential functions come in 2 flavors, growth and decay. So this is a picture of 2 to the x, and it's got that same curved appearance that we predicted when we were looking at the salary example.
They're not lying.
That it only comes in 2 flavors?
No, I mean,
Oh, no. Oh, I get you. Nope, no lies. No lies. So 2 to the x is exponential growth, right? So 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4. So this is how we come up with the points for this graph. 2 cubed is 8. So this is my exponential growth picture. You have exponential growth when your base is bigger than 1, right? In this case, my base is 2. So I have growth. B is called the growth factor again. And then you have decay when the base is between 0 and 1. So in this case, my base is a half, right? So I actually am getting smaller. When you're going to repeatedly multiply by a half, things are going to get smaller. Right? So that happens when B is between 0 and 1, and we call B the decay factor. So let's look at the picture of exponential growth. F of x equals 2 to the x. What is the domain of that picture? The domain of that function? Negative infinity to infinity. It lives over every x value. Right? So negative infinity to infinity. And then what's the range of that graph? 0 to infinity. It never goes below the x-axis. It's like an asymptote. So 0 to infinity, not including the 0. And the reason you don't include the 0 is because we would have to find an x value where we'd say 2 to what number would give me 0. It's impossible. Yeah, no matter what you try, you can never get 0 out of that equation. There is no number that you can raise 2 to and make 0. There's also no number you can raise 2 to and get a negative number. So my range is 0 to infinity. Is that a 1-to-1 function? Yes, it passes the horizontal line test. Okay, what is its y-intercept? It's at 1, yep, 0, 1. How about x-intercept? Doesn't have 1, yep, it can't get to 0, right? Does it have a horizontal asymptote?
Yes.
Yes, the x-axis. There is a horizontal line that the graph approaches but never touches. So that happens when y equals 0, which is the equation for the x-axis. And then its end behavior, I'm going to write down using arrow notation. As x approaches infinity, f of x approaches blank. And as x approaches negative infinity, f of x approaches blank. Okay, so let's look at the picture. As the x values move to the right, what's happening to the y values? They increase to infinity, yeah. And as the x values move to the left, what's happening to the y values? Decreasing to negative infinity or to 0? Yeah. So my end behavior is infinity to the right and 0 to the left.
So that's determined by the y value.
Yeah, it's the y value that the function is approaching. Yeah. All right, let's answer the same questions for the decay graph. What's the domain of this picture? Negative infinity to infinity. It still lives on all x values. Okay. And what's the range? Still 0 to infinity. It still always stays above the x-axis. Is it 1-to-1? Yep. What does it mean that a function is 1-to-1? What information does that tell us? Its inverse is a function. Great. We're going to talk about the inverse of this function on another day, but we do know that it has an inverse that is also a function. Y-intercept of this graph? Also 1, 0, 1. And the x-intercept? None. It never touches the x-axis. It has a horizontal asymptote, also the x-axis, y equals 0. And the end behavior is just the reverse of what it was for growth, right? As we go all the way to the right, the y values are approaching 0. And as the x values go to the left, the y values go to infinity. So we just have to reverse these two. So we say as x approaches infinity, f of x approaches 0. And as x approaches negative infinity, f of x approaches infinity. All right, that's it. Yes.